Hello everyone. In this lecture, we are going to start a new topic, and that is integral transforms. And in particular, we will focus on complex Fourier transforms, which is one form of many integral transforms that are available for solving partial differential equations. So before going to how we can use these integral transforms and especially Fourier transforms, I'm going to give you a brief introduction of what and how these integral transforms are used in solving partial differential equations. So the main method in the integral transforms is that the first thing that we do is we transform the PDE, partial differential equation, into a different space. So we take or transform the PD into a different space, for example, a frequency space, and then in the next step, we solve the transformed equation So we solve the transformed equation in in a different space, like in frequency space. And the reason we can do that is when we transform the PD into a different space, and we are going to show that the PDE is going to become a simpler equation, so we can have we can easily solve that transformed equation in the new space. Okay, and then once we solve this equation, we return back the solution into the real space. Okay, so we transform the solution back into regular space, in the original space that we had the equation for. So this is the main method and the main steps we are going to take to use integral transforms in general. It's not just about complex Fourier transforms. It's a general thing. The steps that we are going to take in order to solve a PDE using these integral transforms. And complex Fourier transform that I'm going to introduce is just one of these integral transforms. We have many of them, like Laplace transform and other type of integral transforms. Okay. So with this brief introduction, let's get started with the and in this course I'm going to only introduce you one integral transform, and if you're interested, you can take a deeper look at Laplace transforms and other transforms. But this is just to give you an idea what this method, which is very common method for solving PDEs. So we are going to start complex Fourier transforms. And these come from Fourier series in the discrete form, but here I'm going to directly jump to the integral and continuous form of that. So the theory, I want to talk a little bit about the theory, and then after that we are going to cover some properties of this integral transform, this complex Fourier transform. And after that, we're going to solve some examples, some PDEs using these complex Fourier transforms. Okay. So theory. So I want to write a general statement about these complex Fourier transforms. In general, we can write any function with some properties by using these integral transforms, in particular in these complex Fourier transforms. Okay, so it can be shown that an arbitrary function fx may be represented in the infinite interval of minus infinity and x between minus infinity and infinity in the following form. Okay. So we can show that we can write and represent fx, any function that has a specific condition that I'm gonna say is we can represent it as this 1 over 2 pi. You can write it as this integral of minus infinity to infinity of e to the minus I beta x times the integral of minus infinity to infinity of e to power I beta x fx dx, and this one d beta. Okay, I'm gonna go through what this means. But these, as you see, they are two integral transforms. So we have transformed these fx using this integral transform, and then we again transform the resulting function using this transform. Okay, and once you transform these, you are going to get your original function fx. Okay. So there is only one condition for this, and that is for f should belong to L1 norm of minus infinity to infinity, and if the magnitude of f goes to 0 as x magnitude of x goes to infinity, or in other words, the limit of x2 plus minus infinity of fx is 0. So if we have this condition, we can write this kind of formula and represent f based on this formula. Okay, so let me say what does this mean. And these are actually two integral transforms and two actually complex Fourier transforms. So I'm gonna go through all of these one by one, and about I, like what is I, I'm gonna define that if you don't know, but this is a complex number, and some properties of these, we are gonna talk about them. Okay, so the first thing I want to say is integral transform here. So here we have integral transform, or so let me before that write something, a note here, and then we can write that. So these constitute a Fourier transform. A Fourier transform pair as the following. So these constitute a Fourier transform pair as this that I'm gonna show. So let me first write this here. So we have an integral transform. So we show this transform, or this is also called Fourier transform. It's one type of integral transforms. We show this with hat. F hat of beta is the representation of fx in the frequency space or in beta. Okay, in minus to infinity of e to power I beta x and fx dx. Okay, so it's a very simple Fourier transform. Okay, so this one we show this also in the operation in the operator form. We show this as this. So I am showing f hat equals to, and this is Fourier transform. I just show it in the operator form with this. This is just this integral that you see here. Okay, so this equals to, and this is called a Fourier transform. So this is Fourier transform. Okay, so if you look at it here, this is actually the first this part, right? This part of the transform. So here it is just a Fourier transform, right? An integral transform or a Fourier transform. This looks like this one if you compare these together. Okay, so this is this part which we call integral transform, and what it does is f beta or f hat beta is fx is just a representation of fx in frequency space. Okay, we call this frequency space. So sometimes you might see this this is nomenclature. It might be different. For instance, if you look at some books, they might define it as integral of minus infinity to infinity of e to the minus I omega x fx d omega, right? And omega is like frequency. So this is other definitions. Okay, but and even you might see they put 1 square over 2 pi here. So here we just stick with this definition. But these just so you know, these are other definitions that we can have. Okay, so this is the integral transform, and then here we had another transform too, another equation here too, right? Another expression here too, and that is what we call inversion formula. So inversion formula. So in the inversion formula, we get fx back from return back or turn back the fx from the frequency space to regular space. Okay, so this was this is the inversion formula. Okay, so this is written as this. So we get back fx. So fx is 1 over 2 pi integral of minus infinity to infinity of e to the power minus I beta x f hat beta and let me just check one thing. The beta. That is correct. Okay, so here what you see is we now have an inversion formula where we take back that f from the frequency space to this frequency from frequency space to regular space, okay? And this is the inversion formula for that, and the operator form of this is shown as this. So we say f equals to Fourier transform, and we show it this because this is inverse, so we show it with f to the power minus 1 of f hat. Okay. So now this formula that you saw here is just, I am going to write it down here, just says fx equals to, so this one is f hat, right, from here. You can see f hat, f to the power minus 1, sorry. So it is like f minus 1 of, this one is the Fourier transform. So this is going to be f of fx, right? So this expression is just that. So we can say, we can represent f with this integral transform, complex Fourier transform, and its inverse formula, take it back to the regular space, okay? So let me clean that. So these are some definitions, right? So this is the integral transform, Fourier transform, complex Fourier transform. This is the inversion formula for that, where we go from frequency space d beta to the regular space. Okay. So I want to make some notes here. So just one note, and then we are going to go through the properties of this Fourier transform. So notes. So if you don't know, I here is a complex number, and this is, you need to know from your calculus, is square root of minus 1. Okay, so this is the definition of I, or you can say I square is always minus 1, right? This is a complex number that we define. And then this has a expression that we can write. This has a kind of mathematical expression that we can prove, but this is, I just show it here. I just write it down. This is very important property of this e to the to I, or complex number, and that is e to power plus or minus I beta x equals to cosine beta x plus minus sine plus minus I sine beta x. Okay, so this is very important property. This is actually how you can reduce this I to these cosine and sine functions. Okay, so these were just some reminders if you don't remember these basic things about exponential and I complex number. And now I want to talk about some properties of Fourier transform. Okay, so up to here, it was just some definitions that we made, and now I want to talk about some of the properties of these Fourier transform that you can use to solve PDEs. Okay, so the first property is the linearity of this operation, an operator, Fourier transform operator. Okay, and linearity states that the Fourier transform of alpha f of two functions plus gamma g, if you just multiply alpha and gamma to two functions and then you add them together, this equals to alpha of f, the Fourier transform of f, plus gamma, the Fourier transform of g. Okay, for alpha and gamma belonging to real numbers. And the same thing for the inverse formula. You can say f to the minus 1 of alpha f hat plus gamma g hat equals to alpha f minus 1 of f hat plus gamma f minus 1 of g hat. Okay, so this is the linearity property, and you can simply prove that by just putting these into the definitions here and here. So they have very simple proof. You just substitute them into the definitions and you are going to get this linearity property of Fourier transforms. Okay, so the second property that I want to mention here is transform of derivative. And this is very important, because, and you see the beauty of these Fourier transforms here. So this property states that the Fourier transform of derivative of a function, or df of x, we are going to find a relation for that. So let's see what it is. So the Fourier transform of it, based on this formula that we have, is going to be e to the I beta x times fx, right? df over dx. So it's going to be integral of minus infinity to infinity of, instead of f df over dx, I'm going to just write f prime x to show the derivative, and then multiply by e to the I beta x dx. Okay, so let's see what it is, and I want to find a property for this. So I'm going to write this as equation 1. Okay. And now I want to use a trick, an interesting trick here, and you can use this too in other type of problems. So what is the integral of this formula? So if I say d over dx of fx e I beta x dx, what it is? Just think about it. Yes, so if you take the integral, because this is a derivative of a function, right, with respect to x, so you are just going to get that function. So it's going to be fx e to the I beta x from minus infinity to infinity, right? So this is the answer of this integral. And let's open this integral and see what are these two terms. So let's open this derivative. So it's going to be integral of minus infinity to infinity. I'm going to use the derivative first, going to be f prime x, the derivative of the first function multiplied by e to the I beta x, right? And this is from your calculus. And then plus fx multiplied by the derivative of the second function, which is going to be I beta times I beta e to the I beta x, right? And this times dx. Okay, so let's see an interesting point here. So what it is, we can see it here, right? Exactly the same formula. So this is gonna be, this term is gonna be from from 1, this is just a Fourier transform of df over dx, right? So we can say that the Fourier transform of df over dx equals to this right hand side, and then I take this to the right hand side, fx e to the power I beta x evaluated at minus infinity and infinity minus this term, which is gonna be integral of minus infinity to infinity of I beta fx e to the I beta x dx, right? Okay, so let's evaluate this. So this one is gonna be 0. Why? Because of the definition of Fourier transform as this. So let me just write that down. So this term is going to be 0 because the limit of x to plus or minus infinity of fx is going to be 0. And this term what it is, just let's take a look at the definition of Fourier transform. E I beta x times fx is gonna give me the Fourier transform. So if I just take out I beta, I'm gonna get integral of exactly this, e to the I beta x times fx, right? E to the I beta x fx dx, right? Exactly this. So this is just a Fourier transform. So this is gonna be I beta f of f, the Fourier transform of f. So very interesting formula. We found a very interesting formula, and that says that the Fourier transform of f prime, the derivative, is gonna be minus I beta, the Fourier transform of the function itself. And you can similarly show that the Fourier transform of higher derivatives, like second derivative, third derivative, fourth derivative, is going to be minus I beta to power k of the Fourier transform of the function itself. This is very important property of Fourier transforms that makes it very useful for solving PDEs. And as you see, differentiation in X or regular space becomes differentiation at X space becomes multiplication in beta space or frequency space. So what does this tell us? This tells us that if you have a very difficult high order PDE, say like df, let's say like 4 to dx4, you can just take the Fourier transform of that equation, ODE, and this is gonna become I beta to power 4 times the Fourier transform of the function itself. Much easier, right? And the Fourier transform of the function itself, you can just write it as f hat, right? So this is going to become like in this Fourier space, it's going to be I beta to power 4 of f hat of beta. And then this is going to give you another PDE or ODE that is much simpler to solve, right? Because you have you got rid of these high order derivatives, and this is just gonna be I to the power 4, which is gonna be 1, and then this is just beta 4, right? So this is a simple multiplication in beta space, and it's much easier to solve this equation rather than having these fourth order derivative, right? Okay, so these were just two properties, and then I want to define some other properties.